So welcome everyone to this workshop on pure theoretic and algebro-geometric aspects of S-Wavy mirror symmetry, held on Zoom as is the norm these days. And it's my pleasure to start with our first talk today. Let me introduce our speaker. Sushmita Venugopalan will be talking about tropical Fukaya algebras.
Thank you. Thank you very much for inviting me to talk as the very first speaker of the online conference. My talk is entirely about on the holomorphic curve side of the mirror symmetry. And it's called Tropical Fukaya Algebras. It's based on my recent paper with Chris Woodward. And the talk is going to substantially overlap with the Western Hemisphere talk in case there is an intersection in the audience. Okay, as the organizers told me, I'm going to start at a very keep it very basic in the beginning, in the first half an hour, and hopefully also till the end it's basic enough. So I start by defining an operation called symplectic cut in symplectic manifolds. And it goes as follows. You have a symplectic manifold, and given a hypersurface, which means it's real codimension 1. And further, there is a Hamiltonian S1 action in a neighborhood of the hypersurface. So if you're given these inputs, you can apply a symplectic cut, and the output you get is two manifolds. So, and what the operation does is it cuts along the hypersurface and mods out the hypersurface by the S1 action. And this turns out to be a smooth symplectic manifold by results of Eugene Lerman. And it has the Z mod S1 as a symplectic submanifold. It's codimension 2, so we'll call it a relative divisor. And it's going to be there in both the pieces that we produce. X plus and X minus are going to contain Y as a codimension 2 symplectic submanifold. Okay, the first example of a symplectic cut is just the blow up of a point. So if you have a symplectic manifold, you take any point P, you take a Darboux ball around it, and you mod out the boundary of the ball by the S1 action. So the separating hypersurface is the S2n minus 1. This is the separating hypersurface. And you mod that out by the standard S1 action. And then what you get is two pieces. The outer part of the ball gives you the blow up. And in the inside of the ball is just the 2n ball with the boundary modded out by the S1. So that is that's a CPN. That's a typo over there. Sorry, this is CPN. And the relative divisor in this case is a CPN minus 1. Sorry, that's another problem. Yeah, so a couple of typos over there. Okay. If you're an algebraic geometer, a way of thinking about symplectic cut is as a degeneration. So if you have a family of smooth varieties degenerating into a singular space with a normal crossing and two irreducible components. So that's an example of a symplectic cut. So the simplest example is, for example, if you take the curve xy equals t sitting inside P2, then the hypersurface along which you're doing the cut is mod x is equal to mod y. And so this when you do the cut, it gives you two pieces. X plus is a line and X minus is another line. Okay, so now we go and generalize this procedure. So what we are going to do is, instead of doing one cut, we are going to do multiple cuts. So which means that in the symplectic manifold X, we have a collection of hypersurfaces and an S1 action in the neighborhoods of each of these hypersurfaces. And we require that in the intersection of these hypersurfaces, these S1 actions are consistent in the sense that they fit together into a Hamiltonian torus action. So, you know, a simple schematic example is here. If Z1, Z2, Z3 are your hypersurfaces, so these are not separating hypersurfaces anymore. And in the neighborhood of each of these, you have S1 actions. And in the intersection, which is Z0, you have a torus action. You have an action of a two torus, and the three individual S1 actions are produced by restricting the torus action. So if you have an input like this, it's in a fairly natural way, you can define the multiple cut operation. So the output is a collection of cut spaces. So what you do is, just as in the single cut, you disconnect the manifold along these hypersurfaces, Z1, Z2, and Z3, and mod out each of them by S1. So the corner Z0 gets modded out by T2, because in each of the pieces we would have modded out by two S1s. So we get three spaces, each of which happen to be smooth manifolds, and these hypersurfaces modded out by S1. These are all divisors, and they are normal crossing divisors in each of the pieces. So in the cut space that we have, if you take one of them, say X1, it has two divisors, Z1 mod S1 and Z2 mod S1, which both of which intersect, and Z0 mod the two torus. Any questions? So the question we are going to ask ourselves today is, can counts of holomorphic curves in the original manifold X be expressed in terms of holomorphic curves in the broken manifold? So I haven't quite defined broken manifold yet, but it's something which naturally comes out of these cut spaces, which I defined in the previous slide. So just have those cut spaces in your mind and think of holomorphic curves in those. And the question is, are they related to the holomorphic curves in the bigger manifold? And we ask a further, more ambitious question, which is that can the counts of these curves, can it be expressed in terms of a sum of products of curves in the broken manifold? So as you can see, this is more ambitious than the first question. Okay, so the main objects, we have three main objects of interest, which we talked about in the previous slide. I'm just going to give them names now. The first one is unbroken maps, which are standard pseudo-holomorphic maps living in X, which is our original manifold, and whose domains are, of course, allowed to be nodal curves. The second object is what we call broken maps. So these are maps, again, whose domain is a nodal curve, and different components of the curve maps to different components in the broken manifold. So the broken manifold, I just told you, it's closely related to cut spaces. In fact, it will turn out that, yeah, let me just keep that for later. So just think of, we had these cut spaces X1, X2, and X3. You have different components of your map mapping to different pieces, either x1 or x2 or x3, and they satisfy certain matching conditions at nodes. So these are expressed in terms of relating maps and living in different components, which is slightly different from what you're normally used to in terms of stable maps. And so these broken maps are additionally equipped with something called a tropical graph, which I'll describe. But notice that there is a matching condition at the nodes, which prevents it from the object from being a sum of products. So we'll also define a new object without the matching condition, which is called split maps. Anyway, that's just a quick map of how the talk is going to be. So the questions can be restated as follows. We are trying to relate unbroken maps, broken maps, and split maps. And so in the first part of the talk, I will go from unbroken to broken. So a good part, a chunk of it will be covered in the first half an hour of the talk. And the second half will be exclusively in the second half, like after the break in the talk, which is going from broken maps to split maps. Okay, so let's explore this unbroken to broken problem in case of a single cut. And before I start, let me tell you that this is what goes in the literature in the name of symplectic field theory. So this is what one of the references which I provided was paper by Hofer and collaborators, which is exactly this, and this is being studied by many people, and it's fairly well known to a lot of people. So, but let me still go through it to motivate how things work in the multiple cut scenario. Okay, so our goal is to kind of get a correspondence between curves in X and curves in the broken manifold. So in order to get that correspondence, we are producing a homotopy. So to produce a homotopy from X to the to its broken counterpart, what we'll do is we will equip X with a family of almost complex structures, which in this case is called J nu. And so J nu is an almost complex structure under which it looks as if this neighborhood of the hypersurface has a neck of length nu. So which means that J nu is such that the neighborhood of Z is a fibration of this form, whose fibers are holomorphic cylinders of length mu. So as mu increases, as the neck, when I mean by the neck of the length, I mean the length of these holomorphic cylinders which occur in the fibration. Okay, so if you are going with the degeneration picture, the way to think about it is you have this family of curves xy equals nu inverse. So nu inverse is so nu, if nu is the neck length, the curve to consider is xy equals nu inverse. So as you change nu, the symplectic form remains unchanged, but the complex structure changes on these curves. And in the limit, as nu goes to infinity, you get the singular curve. So that's the picture. And so since we have this continuous family of almost complex structures, whereas the symplectic form remains the same, we can say that the moduli space of these J nu holomorphic curves are homotopy equivalent for any pair of nus. And the question we are going to ask ourselves is, what happens when mu goes to infinity? Because that's no longer a complex structure on X. So, and this is a result from SFT, symplectic field theory, which says that if you have a sequence u of curves in these neck stretched manifolds whose area is bounded, then a subsequence converges to a broken map. So let me explain what a broken map is and give you a sense of this convergence that's going on here. So this is a picture to have in mind. So we have curves in X in the left side, and these converge to curves in the middle picture, which look like this. So what's happening here is that a part of the curve may collapse into the relative divisor. So if you may want to go with this picture of these conics here. So, you know, a part of the curve will converge in X plus, part of the curve will converge in X minus, and some of it may collapse into this intersection, which is the relative divisor. And in our case, we think of it as the neck region. So in the limit, some curve components collapse into the relative divisor. Think of these as lying in the neck piece. So the right target space to consider for the limit curves is called a broken manifold. So it not only has X plus and X minus in it, it also has the middle cylinder, which we saw in the previous slide, but compactified. So the middle cylinder was Z cross R. So at both the infinite ends, we compactify it and make it into a P1 bundle over the relative divisor. So a broken map consists of components in X plus, X minus, and the neck piece, which is this P1 bundle, which I described. Questions so far? Okay. Now, so I mentioned earlier that these maps have to satisfy matching conditions on nodes. So in case of a single cut, the matching condition is fairly straightforward. What the matching condition says is that if you have a node, then both the lips of the node should map to a relative divisor in the piece, and they not only that, they should map to the same point on the relative divisor. So here I say that U plus evaluated at the node and U minus evaluated at the node are the same point on the relative divisor. And further, the intersection multiplicities at the lift of the node are equal on both sides. So that's all. That's all the matching condition is. And how do we get a matching condition like this? Because, you know, these U plus and U minus are lying in different manifolds. So how do we get this matching condition? And we get it because the nodes are formed by the convergence of long cylinders with small area. So if you look at a sequence of cylinders which are lying in Z cross R, then a subsequence would converge to a node. So the following picture is helpful. So let U nu be a sequence of long cylinders whose projection to Y have small area. And if that is so, then we can say that U nus are asymptotically close to a trivial cylinder. And what is a trivial cylinder? The pink here is a trivial cylinder. It's something that projects to a constant on Y. And so it just lies on a C star fiber and it's holomorphic. So there aren't too many choices. It's just a multiple cover of this one of the fibers. So let's say it's an N cover. Then in the limit, what you get is a node whose intersection multiplicity with the relative divisor is N. And so in general, the way the compactness proof works is if you have a sequence of curves mapping to these neck-stretched manifolds, then a converging sequence looks like what I've drawn in the picture. There are pockets of high area separated by long cylinders of small area. And a pocket of high area converges modulo a translation in the target space. Remember that the target space here we are talking about is Z cross R. So we need to move it up and down in R in order to get convergence. So for example, if one of these components, this one of these pockets of high energy, which is labeled 5, we may have to move it by a sequence of numbers t nu 5 so that it converges in Z cross R. So Z cross R, the non-compact direction is just R. So if you are allowed to adjust your R component, you will get convergence in a subsequence. Okay, so along with the convergence, we have some additional data here, which is uh, these limits over here. For each component, we have a sequence of translations. And if you look at the sequence T nu by nu, that gives you a relative position of the component on the neck. So the components which lie in either x plus or x minus are going to map to the endpoint of this line segment. And the ones in the neck pieces will get mapped to somewhere in the middle of the line segment. So we obtain an embedding of the domain graph into the interval 0, 1. And this is the nascent idea of a tropical graph, which is not so interesting in this one-dimensional picture, but is very useful in the multi-cut situation.
I have a question.
Yes.
How do we know that the rescaled times, this Ti nu over nu, converge, say, to distinct values for different stages? Could it be that some necks become, say, quadratically larger than others?
Yeah, it could totally happen. So in this in what I've said so far, you could just end up some of the neck pieces could also get mapped to the endpoints, or
so in fact, it's not quite an embedding, right? Because some
it's not an embedding at all, because even the picture I've drawn, it's not going to be an embedding.
Oh yes,
so
okay.
Yeah.
Okay.
Okay, so let's take these ideas and go and look at what happens in the multiple cut situation. So this is the picture I had drawn a few slides ago. Just to convince you, let me go there. This is what you saw earlier. Okay, so underlying a multiple cut is a polytopal decomposition of Rn. And this was the first example of a multi-cut that we saw. So, and when I say polytopal decomposition, I think of it as a set of polytopes, which is closed under intersections. So we have these top dimensional polytopes, P1, P2, and P3, and I'm also going to throw in the intersections. So that gives me 4 more polytopes. So that's the polytopal decomposition. So more precisely and formally, the input for a multiple cut is a tropical Hamiltonian action, which I defined. So what we have is, to think of Rn as the dual of torus V algebra. So you decompose that into polytopes, which are Deleuze polytopes. And we have a map from our space X to this part of to the dual of the V algebra, whose image looks like what I've drawn over there. Okay, so and the separating hypersurfaces are the inverse images of the codimension 1 polytope. So in this case, P1, 2, P2, 3, and P3, 1 are codimension 1 polytopes. So their inverse images give you the hypersurface along which you're going to do the cuts. And in a neighborhood of these hypersurfaces, the component of the tropical moment map, which is normal. So for example, if I take P12, so the component of the moment map, which is normal to P12, should generate an S1 action. So just that part of the moment map is an honest moment map. The rest of it it doesn't matter. It can just be whatever map. But in these regions where we are doing the cut, phi is actually an honest moment map. So in particular, in the neighborhood of the P cap, phi is, and all of phi is an honest moment map. Whereas in the neighborhood of these hypersurfaces, it's just some component of phi is an honest moment map. Okay, but I'm going to use this as a running example for the section of the talk, which is if we do two single cuts simultaneously, two orthogonal single cuts simultaneously, it's a multiple cut. And it's a polytopal decomposition, looks like what I've drawn there. So these are the set of polytopes which occur in the polytopal decomposition. So you take P1, P2, P3, P4 and all their intersections. So when you do the cut, you get 4 pieces and these relative divisors. Okay, and we do an analog of neck stretching here. So along the divisors, you stretch in one direction. So we had these 4 divisors. This was x1, 2, x1, 2, x2, 3, p4, and so on. We stretch in one direction. And as a consequence, the intersection of the divisors gets stretched in 2 directions. So the neighborhood of the P hat here, P cap, it gets stretched in 2 directions. So the wide region is stretched in 2 directions. So when you stretch, you go from the picture on the left to the picture on the right. And in particular, if you look at any of these gray regions, it's a fibration whose fibers are cylinders of length mu. So the middle region is going to be a fibration whose fibers are a product of cylinders of length mu. Okay, and we do an analog of the SFT compactness in the setting, which is that if you have a sequence in the sequence of holomorphic maps, a bounded area in these next-stretched manifolds, then a subsequence converges to a broken map. So there has been similar work done before, and I won't go into the details of the what these various works are, but so work of Brett Parker is the closest to what we have done, although it's in a very different language of exploded manifolds. So the picture that we drew in case of a single cut, we get a very similar picture of a convergent sequence in multiple cuts also. So you can guess what's going on. We have these pockets of high energy separated by long cylinders. So this is what a converging sequence looks like. And so the right target manifold, called the broken manifold, is also, you can also think of that in an analogous way to the single cut case. So the original cut spaces, the dark gray ones, the XP1, XP2, P3, and P4 are just the original cut spaces. And the others are thickenings. So these light gray ones, these are thickenings of relative divisors. So these have just been thickened in one direction. So these are P1 bundles. And the intersection of the divisor is XP cap, which has been stretched in 2 directions. So it's a P1 square fibration. So in the general case, to go from the cut space to a broken manifold, you replace the lower dimensional manifolds by thickenings, which are toric fibrations. And because we chose these thickenings to be toric fibrations, there is torus actions on the fibers. In particular, the cut spaces just have the trivial group acting on them, and the thickenings of the divisors have a C star action on them, and the intersection of divisors have a C star square action on them, and so on. Okay. And before I can define, so a broken map, as I have said earlier, comes packaged with a tropical graph, and a tropical graph lives in a dual complex. Earlier, the target space, the tropical graph lived in a line segment. So if the natural guess for doing two cuts together would be to say that it lives in a product of two line segments, which is a square. But in general, it lives in a dual complex, which is going to be a polytope. So, and sorry, a complex. And what it is the dual complex consists of a complementary dimensional polytope P dual for each polytope P in the polytopal decomposition. So the cut spaces will just get points, and everything else will be of complementary dimension. Can I take like 3 or 4 minutes to stop?
Yes, that's fine. We're
Okay.
flexible about when we take a break. Go ahead.
Okay, good. Okay, so I'm ready to define a broken map. So it's analogous to the single cut case. So the domain is a nodal curve modeled on a graph gamma, and each component of the nodal curve maps to a piece in the broken manifold, and there is a matching condition on the nodal points, which I will talk about after the break. And the broken map comes packaged with a tropical graph or a dual tropical graph. And this tropical graph is just going to be a combinatorial invariant. I don't really explain that. You can ask me that later. And so I showed you this example, kind of this picture of a converging sequence. So the easiest thing to think about is the limit. What is the tropical graph of the limit of this kind of a sequence? So if you start out with a converging sequence, which is of this form, you get a limit whose tropical graph looks like that. So yeah, I guess that's just a visual comment. So, a very like a simple example of a broken map is, suppose you have two components in your map, one of them in XP1 and one of them in XP3. So the dual graph is going to be of this form. So wherever the component lies, you put the vertex over there and you connect it by an edge. But an important property that this dual graph needs to satisfy is that the slope of the edge gives you the intersection multiplicities at the node. Being slightly imprecise here, so actually here by slope I mean a quantity consisting of two positive integers. And that is exactly the intersection multiplicities. It's not quite the slope, but it's some data which comes packaged with the tropical graph, the ratio of mu1 and mu2 is the slope. So it does represent something geometric and visual. So the slope of this edge corresponds to intersection multiplicity. So we have two intersection multiplicities, one with the horizontal relative divisor and one with the vertical divisor. And so one is mu1 and one is mu2, and it's same for U plus and U minus. And the matching condition says that firstly you map to the same point on XP cap, which is same as the matching condition in the single cut case. And additionally, you have another, a second condition, which says that if you do a Taylor expansion in the directions normal to x p cap, then the leading order coefficients are equal. So I'll stop here, and I'll continue after the question and answer break.
Okay, thank you. So first, any questions on the record, and then we'll switch off the recording and or pause the recording for people who feel shy about asking. I do have one question. Maybe this will be clear in the next part. But so do we expect then that these tropical graphs will have a balancing condition at the vertices? Because from what you're saying, it seems like the slope of an edge has to do with the homology class of where the curve kind of decomposes when you stretch the neck inside the torus that acts.
Right. So yeah, so actually it's, they don't always have, it's slightly more complicated than just saying the sum of the outgoing vectors is 0. It is because, you know, like if there is a component lying in P cap here, it's actually lying in a fibration. So, so you also need to add the Chern class in.
I see. So it's only if the vibration is trivial that I would have the obvious balancing condition.
Yes, yes. Okay. Otherwise, there is a Chern class term.
Okay. Any other questions?
Do I talk?
About another, well, I think we say 12:15 should be the end. So a bit less than half an hour. Oh, sorry, depends on what time zone. Right?
A bit.
The next time, that is in 15 mod 30 for whatever time zone in about 26.
So yeah, that's a little less than half an hour. Okay. Okay. So I'll start from where I left off. Yeah, this is where we were. I told you that the matching condition, in addition to having the matching on the corner manifold xp hat, xp cap, it also requires that the leading order Taylor coefficients match up. And this falls out from a similar analysis of long cylinders, because nodes are again formed by long cylinders. So if you have a sequence of holomorphic cylinders with small enough area, so we may think of these cylinders are as mapping to a region which looks like a toric fibration. And so, so the fibers are C star square where these cylinders lie. So that's what I've shown in the diagram. You have the base, which is xp cap, and C star and C star are the fiber direction. So these red cylinders are asymptotically close to these trivial pink cylinders. And what are these pink cylinders? They project to the constant on xp cap, which is the base. And in the fiber direction, the map looks like that. So which means that it's a mu1 cover in one direction and a mu2 cover in the other direction. And as these cylinders get longer and longer, we converge to a node. And the matching condition at the node says that the leading order Taylor terms are the same. And this, if you, you know, it needs a little bit of proof, but it is same as saying that these punctured curves are asymptotic to the same trivial cylinder. So we are making some identifications between the neighborhoods of relative divisors on both pieces in which U plus and U minus live. And once you do that, we are essentially saying that it's the same trivial cylinder. So that kind of falls out from the proof of the convergence. And so before I move on from the matching condition, I also give you another way of thinking about the matching condition, which is that this mu1 comma mu2, which I wrote down, it also generates a one-dimensional complex subtorus in this C star square, which was a fibration. And you can think of the matching condition as if you mod out by that one-dimensional torus, then the nodes match up. So this way of thinking about, the second way of thinking about it is a lot like what happens in the single cut case, where you're just saying that the evaluations agree on Y. So which is same as just modding out by the C star and this and saying that the evaluations agree. And the C star by which you mod out in this case depends on the intersection multiplicities. So the intersection multiplicities give you a one-dimensional torus and you mod out by that. Okay, so another remark is that in the broken pictures, nodes do not nodes do not I'm confused about what to say. Nodes do not decrease the index of the map. So generically, you can have nodes. It's not that by resolving the nodes, you get a higher index configuration. That does not happen. So a very key important role in this picture is played by a tropical symmetry group. So a couple of slides ago, I told you that in the broken manifold, we have, so I remind you that in the broken manifold, these various pieces are toric fibrations. So they have various torus actions. So the tropical symmetry group is defined as the subgroup of the product of these various tori, which preserves the matching condition on the nodes. And essentially, the subtorus is generated by the condition that if you have a node, the two components move only in the direction of the edge relative to each other. So that's what this last line says. If we have a node between V plus and V minus, the difference between them has to lie in the direction of the edge connecting them. And from this description, we can, the infinitesimal generators fall out in a very natural way. And the infinitesimal generators of the tropical symmetry group can be read off from the tropical graph. So the infinitesimal generators of the tropical symmetry group are symmetries of the tropical graph. And symmetries of the tropical graph are the ways of moving the vertices in the graph without changing the edge slope. So in the first graph on the left, we cannot move the vertices without changing the edge slope. So there are no infinitesimal generators, so the tropical graph is rigid, and as a result, the tropical symmetry group is finite. And in the second picture, these vertices can be moved to the dotted vertices, so there is a one-dimensional freedom. So the tropical symmetry group is C star. And notice that if in the single cut, everything lies on a line segment. So if you have more than a single vertex, there is going to be flexibility. So the only rigid tropical graph in the single cut is one with just two vertices. Okay, so the results we prove are in the setting of Lagrangian Floer theory. So we are going to look at holomorphic curves, holomorphic disks, whose boundary lies on a Lagrangian submanifold, and we assume that the Lagrangian submanifold does not intersect any of these necks or the divisors, so it's so it lies in the complement of the relative divisors. And assuming this, the result we prove is that for a large enough neck length, the holomorphic curves in the unbroken manifold are bijective to the broken snaps. So these are holomorphic disks of index 0. So we are focusing on index 0 and 1 case, and for large enough neck length, there is a bijection between the broken and unbroken moduli spaces. And this is just a quick remark. Since we are focusing only on dimensions 0 and 1, all our tropical graphs are going to be rigid, because if the tropical graph is not rigid, the tropical symmetry group is at least C star, and the action of the tropical symmetry group is free, so which means that the moduli space is at least two-dimensional. So in the maps that we are considering, the underlying tropical graphs are always rigid. So the moduli spaces that we get can be partitioned based on the underlying rigid tropical graph. So this is a disjoint union here. Okay, so we define an A-infinity algebra called the broken Fukaya algebra, whose composition maps count broken disks of index 0. And what our results basically show is this bijection, which I talked about in the previous slide. It basically shows that this broken Fukaya algebra is homotopy equivalent to the ordinary Fukaya algebra for the unbroken manifold, the standard one. Any questions?
What were the assumptions on X again? I'm sorry for that.
There are, no, I don't assume any Fano or anything like that. I am just assuming that we have this kind of a polytopal decomposition, and we have the decomposition. Oh, sorry, there is one thing I'm forgetting. I do assume that the symplectic form is rational, because I use a stabilizing divisor to attain, to do the perturbations and attain transversality. So yeah, that's one assumption. So we assume that the symplectic form is like.
But no curvature, for example?
So yeah. Huh? Sorry?
Can there be curvature? Can there be an M0 term? You're saying algebras are equal?
Oh yeah. There is a M0 term. Yes. Yeah. So
what does this statement exactly mean?
Right.
So it's a statement about curved infinity algebras?
Right. So you can define we define a morphism using quilted disks, and there is an inverse, and we show that these are homotopy equivalent.
Okay.
Yeah, there is no issues with defining homotopy equivalence if the algebra is curved, right? I guess, are you worried about this Morikatan element? So basically, we define a morphism from one to the other. So that also takes the Morikatan element on one side, a Morikatan solution on one side to a Morikatan solution on the other side. So yeah, so maybe I should be more specific. It's not just L, it's a Lagrangian brane with a Morikatan element, which is taken to one, a similar element on the other side. Does that answer your question?
Yes, thank you.
Okay. Okay, so I get to the second part of the talk, which is regarding degenerating the matching conditions. So I'll tell you why what I mean by that, by using a motivation in the single cut case. So when we have single cuts, our broken maps have this format, and we have matching of the evaluation maps along the relative divisor. And what that means is that the moduli space is a fibered product. So we have a space of curves in x plus and some curves in x minus, which evaluate to the same point at the node on y. So that's a fibered product that we are looking at. But the question we had asked ourselves is, can we instead somehow think of it as a product instead of a fibered product? So this is something done fully done in the paper by Cherest and Woodward, and following ideas in Bourgeois, which is the 5-author paper. So they show that the fibered product is homotopic to a product via deformation by a Morse flow. Right. So the way this works is, I'm going to describe how this procedure works. The way it works is, first, the step one is to deform the matching condition. So we define something called a T-deformed map, and instead the T-deformed map doesn't have a matching condition, but instead the condition is replaced by a deformed matching condition, which I write here, which is that the evaluation on W plus is equal to the evaluation on W minus flow forward by time t. So flowed forward by a Morse function. So you take a Morse function on the divisor and you deform the matching condition by the time t flow of this Morse function. And it's clear that we are doing a homotopic deformation. So if you define your Fukaya algebra using T-deformed disks versus undeformed broken disks, then you get a homotopy equivalence. And going further, when you take the limit t going to infinity, your length t Morse flow segments are replaced by broken Morse flow lines. So the t deformed map in the limit goes to an infinity deformed map, where the matching condition is replaced by the condition that the two endpoints of the node are connected by a broken Morse flow line. So they pass, in particular, they pass through a critical point of the Morse function. So now we have indeed this infinity deformed disks are actually a product because, sum of products. So the sum is over various critical points of the Morse function. So these two factors in the product can be counted independently. So you take any critical point and you count on the two sides, you count the terms independently. So we indeed have a sum of products. I guess there is some cheating going on here because, it may not just be two components here, but yeah, but roughly this is the idea. But we can't, the reason I told you about all this is to say that we can't do this in multiple cuts, because what can happen is that in case of multiple cuts, these stable and unstable manifolds of the Morse flow may be contained in relative divisors. So generically, when you take the limit, you're going to get bubbles, and so the same ideas don't work. So in particular, one of the pieces can just go into a neck piece, and then you don't know what is your Morse function and what's going on there. So yeah, that's what we first tried to do, and it all got really confusing. So now I get to what we actually do. So there are a few assumptions here which we need in order for the technique to work. So let me not describe those in detail, but let's just keep in mind this example. So the example to keep in mind is that, let me just get to a picture, that there is a piece of the broken manifold, which is a toric variety, and all its, yeah, that's what I say here. One of the cut pieces is a toric variety, and all its torus invariant divisors are relative divisors, which means that there is some other piece which is neighboring along that relative divisor. And the Lagrangian is a toric Lagrangian, which is sitting in this toric variety. So that is the example to have in mind. And we will deform the matching condition on the nodes which are incident on disk components. So if you want to have a picture, let's take this picture, which is what? We take a toric variety and we cut out neighborhoods of torus invariant divisors. So we make a cut close to each of the torus invariant divisors. Okay. So in the middle of it, we have one cut space called xp0, which is diffeomorphic to x, but with a smaller symplectic form. And all its torus invariant divisors are relative divisors, or in other words, they neighbor some other piece. And the Lagrangian is a toric Lagrangian. Okay. So with this picture, let's recall what the matching condition was, which we are now trying to deform. So one of the ways of looking at the matching condition was to just mod out the map by one torus. You know, this one torus which was given by the intersection multiplicities, and then say that the evaluations on the nodes coincide, right? So this was one viewpoint of the matching condition. So we deformed this matching condition by multiplying on one side by a torus element. So this deformation is exactly like the deformation in Cherest and Woodward. So these deformed maps look the same. It's just that the limits are going to look very different. Okay. Any questions so far? Okay. So now what we do is recall that the deformation parameter is lying in a complex torus. So we let this parameter go to infinity. I'm not telling you in which direction, I'll come to that later. So let the tau mu be a sequence of deformation parameters going to infinity, and let u nu be a tau nu deformed map. And we look at what are the limit objects. What we will show is, I'm just going to quickly tell you what we will show, and then through an example, try to make the picture clearer. We will show that the limit objects are something called split maps. And these are maps with no matching condition on the nodes. So when you take this kind of degeneration, the matching condition somehow just disappears. And what we get instead is that these objects have a higher tropical symmetry. So we start out with rigid objects with no tropical symmetry, and we end up with objects with a non-trivial, sorry, I should have said positive dimensional tropical symmetry group. In particular, the codimension of the matching condition is equal to the dimension of the tropical symmetry group. So, you know, when you lose the matching condition, you expect the index to go up, and that shows up exactly at the dimension of the tropical symmetry group. So if you mod out by the tropical symmetry group, you again end up with rigid moduli spaces. And using that, right, so this statement we prove is a homotopy equivalence between these tropical equivalence classes of split maps and broken maps. So that's the homotopy equivalence that we prove. And again, if we do the same thing of defining these infinity Fukaya algebras, the resulting, we give the name tropical Fukaya algebra to these split ones, and we prove a homotopy equivalence. Okay, so that's what we do. Now let me just do an example to show how this works out. So I'm going to take a very particular broken map and see how it gets deformed. And this very particular broken map I'm going to take is the broken map of Maslow index 2. So I told you that these thin pieces are all P1 fibrations. So this is the small red sphere is one of the P1 fibers, which sits above this Maslow index 2 disk. So this is a broken disk of Maslow index 2, whose dual graph is shown on the right. Now, when I deform it, I'm essentially saying that these evaluations differ by tau. So since the U plus is fixed, and the U minus is a P1 fiber, it's a U minus which moves by a distance of tau. So these are the deformed disks. And as tau goes to infinity, what happens is that this U minus heads towards the relative divisor. And in the limit, it maps to the relative divisor. But in the way broken maps are set up, when you collapse onto a divisor, you are actually mapping to a neck piece, which is a thickening of the divisor. So this light gray is a thickening of the divisor, and that's where this red sphere goes. So it's kind of, you find it very believable that there is no longer a matching condition, because this red has just gone on to an altogether different piece. So there is no longer any matching condition. But what we do have instead is that since the small red sphere is in a neck piece, that has a C star action. And so that is what I was talking about. The codimension of the matching condition is equal to the dimension of the tropical symmetry group. So which is, both these quantities are 2 in this example. And this phenomenon can also be read off from, okay, we have this phenomenon of this tropical symmetry can also be read off from the tropical graph, as we have seen before. So since we are on a neck piece, the vertex, the corresponding vertex in the tropical graph, it lies in a higher dimensional piece. Earlier it was in the 0-dimensional P1 hat. Now it is in this thing between P1 and P8, which is 1-dimensional. So it is free to move in this 1 dimension. So that corresponds to this C star freedom. Yeah, so that explains why we have this equality here. And before we move on, I observe that I have made a choice in the direction in which I go to infinity. So I went to infinity in this left side, supposedly, and I could also have chosen the right side, in which the case the small red sphere would have gone to the right. So if I, for example, if I do that, if the deformation parameters approached infinity in the opposite direction, then this is what my limit would look like. This red sphere would go to the neck piece on the right side. But we don't want to overcount. We don't want to count both the left and the right. Otherwise, we won't get the homotopy equivalence. So therefore, to prevent an overcount, we should not count both of them. So we include the direction of approach into the data of the split map. So that's the direction of approach. So yeah, I was going to do one more example in detail, but I think I've run out of time. So I'll kind of jump over this discussion, which you can look at the slides later and of course come back to me with questions. I hope the slides are somewhat explanatory. So, you know, with all this machinery, the result we end up proving is that in that picture we had with where one of the pieces is a toric variety, we can say that all the toric Lagrangians in that piece are unobstructed. And the way to prove is these homotopy equivalences between these different Fukaya algebras. And we use the tropical one to prove the unobstructedness. we show that in a split map, the moduli space of the disk part is invariant under the action of the compact torus. So that's what helps us prove the unobstructedness. And this is, so this result here is a generalization of the result of Fukaya and collaborators. So this is yet another way of proving unobstructedness of toric Lagrangians. And yeah, hopefully the technique is useful in other situations as well. So yeah, I'll just stop here and we can go on to questions.
Okay, thank you very much. Questions from anyone?
Without asking you to actually give the part of the lecture that you skipped over, can you skip back a slide or two?
Sure. Okay, so I'm
curious. Go back. This.
Yeah, this is where I stopped.
Right. Yeah. Can you go a couple slides forward? There was a picture there that intrigued me, but I'm not sure which slide it was. A few more. Yeah, stop there. So that's the example where we have 4 pieces coming together. And so you're perturbing.
Yeah, it's the same example as before. It's the same example with 2 cards. So what I say in this slide is that typically you get the extra tropical symmetry because of formation of bubbles. So in the baby example, there was no bubbling. Instead, the component was just going off into the neck piece, which is, I like to think of that also as some kind of bubbling. But you're actually, in general, you have, you start off with this kind of a deformed map. And in the limit, you get extra components. So the red one forms this bubble, or it's possible that the orange one forms that bubble. Mm-hmm. So that's how you get your tropical symmetry.
Okay.
So if you look at these tropical graphs, the dotted edges, they don't have any slope condition because they are those unconstrained edges. But the red ones, you can pull or push as much as you want, and that gives you 1 degree of freedom.
Mm-hmm. Mm-hmm.
I had one follow-up question to this, actually, going back to the original picture of a tropical graph or a split curve. So if I understand correctly, that edge that's now free is a dotted edge or something? Like there's no actual multiplicity matching slope condition on that edge once it's split?
Yeah,
or I was a little confused about that.
That's a very good point. Yes, you caught a mistake. This should be a dotted edge.
Oh, okay.
Yeah, there is no slope condition on that. So the V minus is free to move.
Okay, thanks.
Okay, well, thank you again. We'll stop the recording.